We continue in this video our discussion about how to build a deterministic finite automaton equivalent with a given non-deterministic automaton. And in the last lecture, we took a look on how to remove epsilon transitions. So I'm going to pick it up from there, and I'm going to assume now that the non-deterministic automaton that I have is one that has no epsilon transitions. And the only remaining thing for me to do, so I can prove the result, is to show how to remove non-determinism. So, in other words, what I would like to prove is this particular theorem, saying for any non-deterministic automaton, which, remember, has this form, and our transition relation has no epsilon transitions because we showed how to remove those in the previous lecture. So for any such automaton, there is an equivalent deterministic finite automaton. And I'm going to have a constructive proof for this, meaning that I'm going to show you a method for how to build this DFA, meaning that for any example you might take on a non-deterministic automaton, you will be able to build effectively an equivalent deterministic automaton. And I would like to first give you an intuition for how this construction might work. So remember how the non-deterministic automaton is working. So you start from Q0, which is your initial state, and then you read letter by letter. So again, the fact that we don't have to worry about epsilon transition simplifies our reasoning here. So you start from Q0 and you read the first letter from your input. And the point with non-determinism is that there might be several such transitions that you might take with letter A1. And so that might take you to, say, maybe it will take you to state Q1, say Q11 and Q12, and so on, maybe all the way to some state Q1M. And then you are, again, reading a second letter from your input, and again, you might have quite many options. Maybe some of these, really there is only one option, but for some of them you might have several different options. And so on. So you have all kinds of computation branches, and in the end you get to some states, and maybe or let's say P1, P2, all the way to Pn. And the point of this computation is to check whether there is at least one state that's final. So maybe some of these are not final, and if indeed, I mean, all of them are non-final, then you are going to have a rejecting computation. The input word is not accepted or is not recognized. But if there is at least one such state, let's say this one, then you will say, just based on this, the fact that you've reached, in one of the computations, you've reached the final state, and this will give you an accepting computation. So what I'm claiming now, and I would like to show to you, is that this can also be done with a deterministic automaton. So in other words, what we would like to have is we would like to have some sort of an automaton which goes letter by letter from state to state, and eventually reaches some state, and all of these things are done deterministically. So there is maybe state Q1 and state Q2 and state Qm minus 1, and maybe here is state Qm, something like that. And you would like to have this an accepting computation if and only if this one was an accepting computation, meaning if and only if one of these many possible computations was reaching a final state. And I'm going to pause now for a couple of seconds, and I'm advising you to pause this video and think about some intuitive idea about how this could be done. What would be the key insight for these deterministic transitions in such a way that you capture with this one single computation this whole spectrum of computations from the non-deterministic world. So pause this video if you like for a few minutes and think about this. So I can give you now the intuition. What I'm thinking is that we can somehow think about it like this. So we start from state Q0, which is going to be represented in the deterministic automaton just with state Q0. And then after one step, the non-deterministic automaton could be in any one of these. And in fact, each one of these states defines one of several computations. And what I'm saying is that this could be maybe represented here simply by saying, hey, you know what, I mean, these states, all of them from the non-deterministic automaton, maybe I can just write them down, you know, and this will be, in fact, my state. So I'm going to just remember that I can be in any one of these states, just like this non-deterministic automaton was. And here in the second step, you know, I could also be here in many states, and all of these are then going to be represented in state Q2. And you see, I mean, now this is a deterministic computation, but still I can remember the whole spectrum of computations that I was running in the non-deterministic world. And I'm going to make this concrete in just a moment in terms of mathematical definitions. But I think it's important to understand the concept. And finally, when I get to this one, in the same spirit, this is going to be represented in this state. And now the idea is, you know, when do I declare this to be final? So when do I declare this computation to be accepting in the deterministic world? And by now it should be easy to see. I mean, I'm going to declare that this is final in the deterministic automaton if at least one of these states from the non-deterministic one was a final state. And if all of them are non-final here, then this one that corresponds to all of them at once, this one is going to be non-final in the deterministic automaton. So I'm going to make this concrete now and give you the formal definition and then a formal proof that this is working out fine. So the proof now is going to go like this. I have my non-deterministic automaton, and this is made of Q sigma Q0, or in fact, yeah, so Q sigma delta Q0 and F, and delta is included in Q times sigma times Q. And I'm going to build now, so this one is obviously an NFA, a non-deterministic finite automaton, and I'm going to build an automaton which is going to have a different set of states. And in fact, as I have anticipated in my intuitive explanation, this is going to be a state of B is going to be a subset of Q. And I have the same input alphabet. I have the transition function that I define in a moment. My initial state is Q0, but this time I represent it as a set because that's my set of states here. And then I will have some final, so some set of final states here. So my delta is going to be defined on Q, but in my case, this Q is 2 to the power Q. So it's a function from the set of states times the alphabet into the set of states. And so I will define this in a moment, and G is going to be you know, a subset of 2 to the power Q. And so this is going to be a deterministic finite automaton, and I will define it in such a way that they are equivalent. So that's the objective. And so here is how I'm going to define it. I'm going to say that first how I define this transition function. So the transition function is going to be defined like this for a set P. So P is in this one, or if you like, the same thing is to say P is a subset of Q. So delta of P and letter A is going to be defined to be all the states in Q in such a way that P, A, Q is an element of delta for some P in P. And so this is the same thing as saying that I'm going to let's see. So this is the same thing as I can also write it like this. So it's Q in Q in such a way that there is P in P with P goes to Q with A. So if you like, kind of suggestive notation is like this. In DFA, in my automaton B, I will have this transition from set P to set Q if and only if P was going in automaton A to Q for some P in P and Q in Q. I see that, let me just use a different letter here. And maybe for that reason, I also use a different letter here. So maybe P goes to R, and this is for any P in P and R in R, just so that I'm not confusing it with this Q here. So I hope that this is clear, my definition of the transition function. I will go from state P to state R if there was such a transition P to R for some P in P and R in R. And the other part of my definition is going to be, again, as I anticipated when I showed you the intuitive definition, I have to define now the final states, and the final states are going to be all the subsets of Q that have at least one final state from F. So this was the exact intuition we had in the intuitive explanation for this construction. So that's all there is to this construction. And what I'm claiming now is that language of A is exactly the language of B. And I can prove this in the following way. First, I show this inclusion. So I take W from the language of A. And I discuss now two cases. If W is the empty word, remember that my automaton A doesn't have any epsilon transition. So the only way this could happen is if the initial state is also final state. But then that implies that this state, obviously, this is a trivial implication, is non-empty. And what this means is that this state of the automaton B is a final state. So this, in fact, is so in G. So in other words, I'm writing here, it's a final state of the automaton B. So there you have it. This is the initial state, but it's also a final state. And so that means automatically that epsilon is in the language of B. Now, if W is of the form A1, A2, something like that, an, with n greater than or equal to 1, and all these being letters, then I'm going to, just on the next whiteboard, I'm going to consider all the computations in automaton A with this input word. So in this case, in automaton A, the way it goes is I'm going to start with Q0, and with letter A1, I could have any one of these transitions. And this would lead me to state Q0, Q1, 1, and Q1, 2, and maybe something like Q1, I1. And I'm building a computation in automaton B, and this is going to be I start from the initial state. And with letter A1, so all of these are in A and all of these are in B. I'm just going to, because this holds, and these are all the transitions you have with letter A1 from Q0, then I'm going to have in automaton B that this is a transition, just by the way we have defined the transition function in automaton B. And then from each one of these, I'm going to take all the options I have from all these states with letter A2. And that's going to give me, so it's going to give me a bunch of states, and these are, so maybe this is Q2 1 and Q2 2 and Q2 I2. So again, I reach one of these states by taking any one of these and going with an A2 transition, and I get these states, and these are all the states I'm getting by taking all possible transitions with A2 from these states. And so because of this argument that I'm taking all of them and I can already reach these ones by going from one of these with A2, what this means is, again, by the way we have defined the transition function, that this is a transition in B. So I go to Q2 1 all the way to Q2 I2. And so it goes in the same way to the last step of the computation, where I'm reading letter AM, and I got to state QM1, and in a different computation with state QM2, and maybe with a different computation QMIM. And so this eventually also in the automaton B, with the same argument as before, it goes to this state where I'm collecting all of these QM1 all the way to QMIM. And I just pause for a moment to point out that this is a state in automaton B. So this is part of 2 to the power q. So it's a state. This is a state. In fact, it's the initial state. So all of these are states. And so obviously what I'm building here is a computation, state by state, from state to state, reading one letter at a time. And remember that the word W was in the language of A, meaning that at least one of these is a final state. So QM I is final for some of at least one between 1 and IM. And so by definition, this is a final state, because this state here is part of this set here. And so this one is included in here. So this is a final state in automaton B. And so this whole thing gives us the conclusion that really the word W has got to be in the language of B, because we just built an accepting computation for W in automaton B. So now going the other way, if I take, so I want to prove now the other inclusion, meaning I want to show that the language of B now is included into the language of A. So again, let's take some word in the language of B. And again, I will have two cases. If this is the empty word, then by definition, remember this is a deterministic automaton. Obviously, there are no epsilon transitions in here. So by definition, this can only happen if the initial state is also a final state. And by the way we have defined this, it means that Q0 intersected with F being the final state from A, is non-empty. And obviously this is the same as saying Q0 is in F, and that's the same as saying the epsilon, the empty word, is accepted or recognized by automaton A. So in this case, it works out. If I have a longer word, let's say this much, and m greater than or equal to 1, and all of these letters from sigma, then the computation of automaton B on W is obviously accepting. So please note I'm saying the computation because this is a deterministic automaton, so there is only one, and so it's accepting. And I want to show this this accepting computation. So from Q0, I'm going to go to some state. Let's say if this was let's denote this by say P0. I will go to a state P1, which is to the power Q with a 1, and then I go to some state P2, and so all the way I go to PM, and PM is a final state. And so now we remember that what this means is that really we have all these. So by the way, I mean, this follows just from the definition of what it means to have this transition in B. So this, it means that we have all of these transitions with A1 to state P11 and P1 I1. And what I mean by this is that this set P1 consists of exactly these elements. So if these are all the elements of P1, the fact that I have this transition, by definition, it means that in automaton A, this was in automaton B. So in automaton A, I have all these possibilities. And again, if P2 is made of states, say, P2, 1, and all the way to P2, say, I2, the fact that I have this transition from P1 to P2, it means that I have transitions from all of these states. So all of these states can be reached from one of these. So I will have here P2, 1 and all the way to P2, I2. And all of these, you know, maybe this is reached from this one with A2, and maybe this is reached from this one. But all of them are going to be reached from one of these states. In automaton A. And so I continue all the way, the point being that I'm just expanding this tree of computations in A, and eventually I get to this state PM. So if PM is PM1, PM IM, the fact that I have this transition from the previous state to this one, it means that I'm reaching in automaton A all of these states from one of the previous ones. So all of these are reached. And now the punchline now is to recall that PM is in G, so that means that this set is in G. And from the way we have defined the set G, it means that one of these, at least one of them, maybe this one here, this one is in F. That gives you the accepting computation. You are going to follow these edges, and maybe you have reached this one from this, and maybe you have reached this one from here, and maybe you reach this one from here. But whichever way it is, this goes maybe like this. And so you find one accepting computation in A. So this implies that there is an accepting computation for W in automaton A, so it implies that W is in A. I realize that there is a lot of letters and a lot of considerations, and I hope that they make sense to you, and especially based on the intuitive explanation I gave in the beginning of this lecture, you will be able to trace carefully all of these arguments. So that's it. I'm wrapping up this video lecture here, but I do continue with one more lecture on this topic, and I'm going to give one example in that final lecture on the equivalence of deterministic and non-deterministic automata.